Going to look at what we call zeros of function in this lesson. Zeros is a concept that you've already seen before. You just may not have called it a zero. You may have called them roots, you may have called them solutions, and they are all essentially the same thing with a little subtle difference between each one. So let's start with zero. We call a zero of a function some value, usually referred to as C, sometimes it's referred to as A, and it's a value that when you plug it into the function, you get the value 0. That's where the name 0 comes from. Plug that into f or g or whatever your function is, and out comes the number 0. 0 of a function. For example, here's a function f of x squared plus x minus 6. We say that 2 is a 0 because if you plug in 2, you get 0. Also, if you plug in negative 3, negative 3 is a 0 because plugging negative 3 into f also gives you the value 0. Negative 3 squared is 9, plus negative 3 is 6, subtract 6, out comes 0. And for this particular function, those are the only two. Any other value that you plug in, you will not get 0. And if I come over here and graph that, let's turn this one off. If I graph x squared plus x minus 6 minus 6, if we graph that, we get that, hey, look, it crosses at negative 3, crosses at positive 2. And those are very important points. Zeros of a function are the transition from where the function can go from positive to negative. It's not always true, but usually it is. Not always, but sometimes it is. Transit here to the function at negative 3 to the left of negative 3, the function is positive. Between negative 3 and 2, the values of the function are all negative. To the right of 2, the function values are positive. So in this particular case, negative 3 and 2 represent a transition from where the function is positive to where the function is negative. They are also important points for another reason. We call them roots of the polynomial. Zeros can also be called roots of the polynomial. This is a second degree polynomial. Highest power anywhere in it is 2. It is a second degree. So that means we can do what's called root extraction. The value of the degree tells us the maximum number of roots that are possible. It doesn't guarantee there will be 2. It says at most there will be 2. Sometimes we get roots that repeat. For example, if we have something like x squared plus 4x plus 4, we would get x plus 2, x plus 2 when we factor that. It's the same value twice. So then in that case, there's only one root. There's a maximum of 2, but there's only one. That actually happens. In this example, the degree is 2, and we actually get 2 roots. We know we get 2 roots because if we factor it, we get 2 unique factors. Each factor has its own unique solution. So we got 2 roots. And finally, we can say that these are solutions because they solve this particular equation. Three names for the same thing. And yes, that gets a little frustrating sometimes in mathematics. You have three names for essentially the same concept. However, each of these has its own unique context. We use the term zero when we're talking about values of a function being that give us zero. We use roots typically when we're setting a function equal to zero and solving. We say solution when we set any equation equal to zero. It doesn't have to be a function. Remember that not every equation is a function. So in that context, we would just call the values solutions. Here's another little sort of reminder, a little more showing the differences. Zeros, we are looking for some value C that gives us the value 0. So we're not solving an equation necessarily. We're simply plugging in some number that gives us the value 0. If we're talking about a root, we are setting the function equal to 0 and solving it for x, or whatever variable is inside here. And if we're using the term solution, we're just solving an equation. That's all we're doing. So each of these has its own unique, subtle context. Yes, they all essentially mean the same thing. But to say that, oh, I'm going to find the zeros of this is technically not correct. You're finding the roots. If you're solving an equation and you say, hey, I just found the zeros, not necessarily. Solving an equation generally does not necessarily mean you have a function. I can solve this equation if I want. I can solve that equation, but that's not a function. This has no zeros. It's not a function. It has no roots because it's not a polynomial equation. Polynomial equations, by definition, are of one variable. This has two variables. This has two variables. I didn't give myself a good equation there. I just gave myself a circle of radius 0. There we go. That's better. I can solve this. I can say x is 3, y is 0. There's a solution. There's an answer. But that's not a root. That's an ordered pair. Ordered pairs are not roots. Roots are single values. It's not a 0 because it's not a function. Here's another solution. Again, it's not a root. It's not a 0. So make sure you understand those subtle differences between the three terms. Going to do several examples here with domain zeros, and I'll even throw in vertical asymptotes for a little refresher. So for each of these upcoming problems, we will find the domain, we'll find the zeros, and find all the vertical asymptotes. And it's probably a good idea for you to try these before I do them. So for each problem, you may want to hit the pause button, try it yourself, and then check your answer with mine. I'll start with the domain. Looking at this function, I have no square roots anywhere. I have no variables in the denominator, so there is nothing that I cannot plug into x. Domain is the interval. Don't forget your interval notation. Interval from negative infinity to positive infinity. Since this is a function, I can find the zeros. To find the zeros, we set the function equal to 0 and solve. And because we are all good students of algebra and have mastered all the concepts of Algebra 1 at this point, you do not need me to run through those steps. 0 is x equals -3. Finally, vertical asymptote. Well, because I look at the domain has no restrictions, it means that there are no vertical asymptotes. And here's another way I can tell. This function is linear. Linear functions never have restrictions. So there are none. No vertical asymptotes here. Next example. What color did I use? Oh, purple. Starting with the domain. I have a rational function here. Rational function. So, that means I'm going to have some sort of domain restriction. And I see that -1 cannot be used. So my domain, -infinity, all the way up to -1, but I cannot use it. So I will union that with -1 starting over here. But again, it is not a bracket. It is a parenthesis all the way to +infinity. And since I did this right away, let me do vertical asymptote right away. We have a vertical asymptote at -1. X equals -1 is our vertical asymptote. Find the zeros. We simply set the function equal to 0. Now you need to remind yourself, how do you make a fraction 0? You know the denominator cannot equal 0. So how do you make a fraction equal to 0? Again, that is an Algebra 1 topic that we need to have mastered at this point. So I know that you can all do those steps. X equals 3 is our 0. X equals -1 is our vertical asymptote, and our domain 2 intervals. Next problem. Now we have a radical function. Find the domain, find the zeros, find the vertical asymptote. So for this one, we're going to remind ourselves that the domain of a square root is 0 or positive. So for this one, I need to ask myself, what value of x is going to make this negative? To find out what that is, we need to set that equal to 0. And we need to solve. Now notice, we get this. What's the square root of -3? Not a positive number. Not a nice number. Not even a real number. So, for this portion, we don't have a solution. What does that mean for our domain? It means there is no value of x that will make this negative. The only way I get a negative number inside is if I have an imaginary number. And since we are confined to using real numbers, there are no bad real numbers. The domain is everything. Negative infinity to positive infinity. No matter what I plug in here to x, I will get the square root of a positive number. Even if x equals negative 72 billion, we're squaring it. Squaring a negative is automatically a positive. And then we're adding 3 to an already positive number. There is no way I will get a negative inside of here. Since the domain is all real numbers, there is no vertical asymptote. To find the zeros, we set the function equal to 0. And we kind of already did that. The only difference is here we have the square root around it, here we don't. But by squaring both sides, we end up here, and again, we get the same problem. X squared equals a negative number. There are no zeros to this function. There is nothing I can plug into x that will give me 0. Nothing. Let's check out how this function looks. I can delete all these. Square root x squared plus 3. There it is. Never touches the x-axis. Remember that when a function has a 0, it is some x value such that f of x, which is also y, is equal to 0. Y is never 0 on this graph. It never touches the x-axis. So therefore, there are no zeros. That doesn't mean it's not a function. It just means it never comes down low enough to hit the x-axis. It also means the only solutions to this equation are imaginary or complex. Next problem. We'll start with the domain. Domain, again, I have to ask myself, what value of x will make this 0? Is there any? And it looks like the answer is no. No matter what I plug in for x, I square it, making it positive. Then it's doubled, still positive. Then 3 is added to it, still positive. Nothing will make this equal to 0. So the domain is like so. No vertical asymptotes. Find the zeros. Set the function equal to 0. We know how to deal with rational functions, solving rational equations. We know how a fraction can equal 0. And I will just say you finish. Because you know what the zeros are going to be. You don't need me to go through these steps. You know what x will equal at the end. 2 zeros. And I will let you fill in the rest there. Same function as the last one, with a twist. Square root. What does that change? Well, doesn't really change a whole lot. The denominator cannot be 0. And because we're inside a square root, the denominator now cannot be negative. Well, that's not a problem. Because this function has a positive denominator always, based on the arguments we used in the last problem. No vertical asymptote. And our zeros end up being pretty much the same values as they were the last time. The only difference is now we have this, which when we square both sides, and you will get the same zeros that you did in the last problem. I'm going to do one more example. Need to copy all this. Paste here. I'm going to alter this problem ever so slightly. I'm going to take away the square in the denominator. Find the domain, the zeros, the vertical asymptotes. So the domain. Because I took that squared away, now we have a potential problem. Our denominator has to be non-zero. And because it's in a square root, it also has to be positive. So I find the value where it does equal 0, because again, that's a transition from negative to positive, or positive to negative. And I get negative 3/2. My little imaginary number line here. I'm going to test a number on both sides, see what happens. So I need a number over here to the left of negative 3/2. Like maybe negative 2. 2 times negative 2 is negative 4. Negative 4 added to 3 is negative. All those values to the left are negative. Choose a number to the right. Let's say 0. Plug in 0, we get a positive. So our domain is going to start at negative 3/2, not including negative 3/2. So that'll give us a 0 denominator, and going all the way to infinity. We have a vertical asymptote. X equals negative 3/2. That value cannot be used. Remember that typically a square root can equal 0. But because this particular part is in the denominator, it cannot. That leaves us to find the zeros. And, oh look, we get the same zeros we got in the last problem and the one before that. Make sure you understand all these examples. Post any questions you have. If you need any more practice problems, let me know.